Let me start recording. Okay. So for the beat, so whenever you see an image, you should start from the equation. So for the beat equation, you need to go to lecture 7. For the beat equation is f0 to omega n square minus omega square psi omega n to t psi omega n minus omega to t, right? So that's the time dependent function or time domain function for your beat signal. So these figures is going to give you the solid line in figure number 2. So a few things, actually 3 things you can get from these function. So first of all, you will know the maximum value of these x beats. It happens when your sine function are 1, right? When your sine functions are in the value of 1, then you get the maximum value because your sine is from positive to -1. It's from minus to +1. So in this range, only when your sine functions reaches 1, you get the maximum value. So that means your maximum is 2 times f0 omega n squared minus omega squared. So that means this point, which is a maximum value in your signal, if you track this solid line in 1 cycle, this is your maximum value. So these values actually 2f0 omega n squared minus omega squared. So remember also, your f0 is the normalized force amplitude, all right? You have to divide everything by m. So that's one way to do it. I think a lot of you actually doing these in a different way. So what you do is, because I already gave you 3 data points, so some of you plug these data points back to this equation and solve these f0 numerically using MATLAB. That's also feasible, but it just like takes more time and not convenient. All right. So that's for the amplitude. The other thing is for the beat frequency. So by definition, beat frequency is the difference between the 2 signals. Okay, that's just a definition, no reasoning. But then how can we get the beat frequency from the plot? So first of all, I think everyone get it correctly. So as you can see here, if you look at the sine waves, we have 2 sine waves multiply each other. So that means if you know how to do signal processing, that's actually called modulation. So if you have 2 sine waves multiply each other, that means your signal actually have 2 frequency components in it. So the first one is the high frequency, and then the second one is the low frequency component. So let's define omega high as half of omega plus omega, and then your omega low is the difference divided by 2. All right. So the high frequency component is really clear over there. So that means the period of the high frequency is omega high 2 pi. So what is this period? So if you track this solid line, if you keep track of it, so you can see that this frequency has a high frequency component, which is here. So this distance is the T high, all right? And then you can also see the second low frequency component. In that case, the low frequency component is actually in the amplitude. That means the amplitude of the high frequency signal is changing gradually over time. And then this is your omega low, all right? So the low period is just omega low 2 pi divided by this. So if you look at these low frequency components, actually, that is your T low. All right, so as you can see here, I think T high, everyone gets that. So for the T low is 2 pi divided by omega n minus omega. Actually want the absolute value, so that you can find the two results. So this is it. And then if you want to replace your beat frequency, let's name it as omega beat, into this equation, then it's actually 2 pi omega beat and 1/2 equals to T low. So the other way to write it is 2 pi omega beat equals to 2 times, actually, oh, sorry. I think I had it wrong. It's actually 1/2 times T low. And then 2 pi over omega, that's another period. We call these as period of the beat, all right? So the period of the beat, use a different color. So this is the period of the beat. If you use a T beat to calculate omega, then you have to use this red equation. If you use T low to calculate your omega, then you have to use this blue equation. All right? And then the other high frequency equation, I think most of you get it correctly. So any thoughts? I think it's just the way I presented it during the lecture. I think it's really confusing. I give you too many frequencies. Hopefully you understand here. Here I emphasize 3 periods: high frequency period, low frequency period, and also the beat period. And then the beat is the frequency difference. All right. And then the third equation is here. Make sense?
So is the beat frequency the frequency of the envelope?
I didn't get your last word. You dropped out.
Is it the frequency of the envelope itself?
Yes, correct. Yes, you're right. The beat frequency is the frequency of the envelope. So your envelope is actually has 2 signals, right? Mm-hmm. If you look at the envelope, then yes, the beat frequency is the frequency of the envelope. But if you only look at one curve of this envelope, then it's actually that frequency is the low frequency, mm-hmm. which is what I'm denoting here.
Awesome.
All right. All right. So I'm going to put 5 points back. So for this problem. So Q2, I think I'm really glad that you know how to use Lagrange's right now. I think most of you is just have a typo here and there. It's usually a sign error. So if you do have questions related to Lagrange's, let me know. And let's talk about these individually. So if you still don't know how to do Lagrange, then you're very likely to fail this class. Okay, Q3. Man, that's I try to save this problem. You can see that I put stars over there because I thought that's challenging, but I think it's too much for this exam. All right. The good news is you already know how to get part 1 and part 2. So let me directly find xs over ys. You just do Laplace transform, move things around. And then you get cs plus k. If you do want to normalize both top and bottom by m, then you get the normalized format. Either way is okay. Okay. So from there to here, you just normalize by m. All right. So you have s over y, that's transfer function. We need to use this one to go to part C. So as I said, the purpose, the function of the reason why we need to find out Bode plot or transfer function is we want to use it to analyze steady state response. So your transfer function has output over input. So input is usually given in the problem. So in this case, our input is the base displacement. For part C, the output is usually given or is usually associated with the parameter of interest. Okay, if you look at part C, it asks us what's the maximum displacement amplitude, x naught. So that means we want to analyze your output displacement x. So that's why your output has to be x, all right? So then you have this transfer function. So if you go to, I think, lecture 11, right? I might have it wrong. So I think it's lecture 11. So over there, we talk about base excitation. Give me a second. Right. I think let me double check. I don't want to confuse you anymore. Is it lecture 11 or 10?
Okay.
All right. So yeah, it's actually lecture 9. So lecture 9, slide 5. You're gonna find the transfer function over there. So over there we have x over y, and then it has 1 plus 2 zeta r squared, and 1 minus r squared plus 2 xi r squared 1/2. Take a square root. So here, this x over y, that's the amplitude ratio. So let's look at what's the amplitude here. So we have our output amplitude x naught. That's something to be found, and then we know that the input amplitude is 10. What's the unit? 10 centimeter. Okay. So then let's look at we already know this ratio in terms of zeta and r. What is your zeta? Your zeta is that just the damping ratio is c over 2 square root mk. So that's from lecture 3 and all previous lectures. So R is a relative frequency. Your omega is the driving frequency or excitation frequency. That's your undamped natural frequency. All right. So omega n is just square root k over m. Your omega is something to be given in the problem description. In this case, your omega is from 3 to 5. It's actually a range. We want to find out which frequency omega maximize your x naught. We already know that input amplitude is a constant. So that means we just need to find out what's the maximum value of this equation, right? When r equals to 3 divided by, let's calculate this out, that's actually 2 radian per second, 5 over 2. So we just need to find out when r is in this range, what's the maximum value of that transfer function. So let's draw it out. So in that slide, I already give you the shape of the Bode plot. You have r, you have x over y, and then it looks like something like this. So this value here is your resonance, r peak. This r peak is actually slightly less than 1. You can assume is approximately 1, but it's actually not. It's slightly less than that. But no matter what, you already know the resonance is around 1. So that means your operation point, that is r equal to 1.5. This is r equal to 2.5. You already know that your operation point is on the right-hand side of your resonance. So that means if it's working on the right-hand side, the higher the frequency, the lower the amplitude. Here, you want to maximize your amplitude. So you want to lower the frequency. So that means omega equal to 3 or R equal to 1.5 gives you maximum X naught, right? So you don't have to calculate these, like, I think some of you actually calculate this point and also that point, and then trying to find the X naught. But if you don't know how to use a Bode plot and how to read it, you can directly find out, okay, R equal to 1.5 is the value. So you just plug in R equal to 1.5 back in, and then you can get your omega naught. All right, so that's for part C. Anything? So any questions for part C? So I think the challenging part is if you need to find out which Bode plot to use. All right, so if you have no questions, if you do have questions, you can also ask me after class. And then let's go to part D and part E. They're actually very similar to part C, but we need to look at the problem description again. So here, the output is no longer X naught. So we care about the P naught. We want to analyze the steady state response for P. So what is P? P is a relative displacement. So it's the difference between X and Y. So in class, we don't use P, we use Z. So if you find Z, then it's actually more familiar with. That's what you're more familiar with. So for part D and E, you have to go back to lecture 10, slide number 2. Over there, I derived the equation, the transfer function for you. So the output is P, the input is still base displacement, and then that's actually the so-called seismometer transfer function. So the amplitude is R naught divided by square root of 1 minus R squared. All right, so as we know that it's the ratio of your amplitude. So that means the output ratio, the output amplitude is P naught, input ratio is 10 centimeters, all right? So the first question asks you, when omega is 5, what is P naught? So R is omega over omega n, and then you already know that omega is 5, omega n is 2. That means your R is 2.5. You just plug in R equal to 2.5 back over there, you get the ratio, and then you multiply it by 10 centimeter, you get your P naught. The most common mistake for this one is, okay, so when you saw the problem description, you see PT equals to XC minus YT. And then we want to find out what the P naught is. So we don't know P naught, but we know X naught, we know Y naught, where Y naught is 10 centimeters. So you just directly find the amplitude from the amplitude difference. So actually that's not true. So the reason why that's not applicable is because this XC is not a constant, it's actually a sine wave. Between these two signals, you actually have phase lag. So that's X naught cosine omega t plus theta 1 minus Y naught cosine omega t plus theta. Because this theta 1 is not the same as theta, if you plot it out in time domain, that's your, let's assume this is your xt, this is your yt. The amplitude of this difference is actually not the amplitude difference. I mean, the signal difference is not the amplitude difference. That's because your signal difference is here. right? The black lines indicates the difference. So this difference is actually changing, and the reason why it's changing is because you have a mismatch between these two signals. You actually have to derive transfer functions for PT directly. So you cannot just use X naught and Y naught to find your P naught. So once you have these transfer function, once you have these P over Y function, you can go to lecture 10, and then you have R, you have P over Y, and then you know the shape of these curve is something like this. So again, this resonance, this RP, is very, very close to 1. And then we said if we want to reduce the steady state P naught, do we want to increase the omega or reduce the omega? So let's first find out where the omega is. So your omega is 5, your R is 2.5. So that means your operation point is somewhere over there. So you have the freedom to either increase it or decrease it, right? We already know that your input amplitude Y naught is a constant. So in order to reduce your P naught, you just need to minimize these transfer function. So if you look at the curve, that means you need to go to the high frequency side. All right, that's how you reduce the magnitude ratio. All right, so I can actually ask you this question in a different way. So what if your omega is not 5? What if your omega is 1.0? In that case, do you need to increase or reduce your frequency? So
Reduce.
yes, we need to minimize P naught. So in that case, you want to reduce the frequency. That's because your R in that case is 1.2, is 0.5. So that means your operating point is to the left-hand side of your resonance. So to further reduce the magnitude, you have to go to low frequency. Right? So it all depends on how you, where the operating point is. So if your operating point covers, I can give you another special case. If your omega is 2 radian per second, you want to minimize P naught. And then you have the freedom to change it by plus minus 5%. Which way to go? So then, where is your operating point? Your operating point is around R equals to 1, is over there. It actually covers the resonant peak. So it's actually in this range. So in that case, you have to calculate these two extreme points and then compare them. So one of them is going to be your optimal operating condition. You see what I mean? So it's not as clear as the red or purple points. In that case, because the shape looks like a curved shape, so the minimum is going to be one of these edges. So you have to calculate these end values and then compare them. So actually, this problem explains how to do how to use body plot for system design. So, for example, if you want to design a car or design a machine, you have the freedom to change the excitation frequency. For example, you have the freedom to choose how fast the motor rotates. then you can choose the motor speed based on this Bode plot. All right, so that's for question 3, part C, D, and E. As I said, in the makeup, I'm gonna put 10 points back. I think most of you are eligible for this problem. So if you do have any questions after related to this, you can send me emails after class. Just make sure you understand everything before Wednesday, okay? Because that's gonna be the only makeup for this problem. So for Q4, I think that's the most common mistake is how to find the amps. So in the class, what we got is right. So that's the equation we got in class. I think it's lecture, which one? Yeah, that's lecture 9. So we need to find out what's the meaning, physical meaning of each one. So the first M here is the total mass on the support. So let's look at this problem. What's the total mass here? We have M, big M, M naught sitting on this mass, the support. So that's why the total mass here is M naught, big M, and small m. So you have to consider everything. So the damping C is the damping of the support. K is the stiffness of the support. So over there is pretty straightforward. So these M naught is the moving, or I should say rotating mass. Over there is just M naught. And then omega R is the rotating speed. You have to convert it to radian per second. So I'm giving RPM over there. So if you have like A RPM, so you want to convert it to radian per second. So RPM means round per minute. So one complete term is 2 pi in radian. And then you have 8 terms per minute, 1 minute, 6 seconds. That's how you convert RPM to radian per second. All right, so you can easily find the omega R. So E is the eccentricity, or how far away your F naught is from the center of rotation. So over there is L. So all the other stuff applies. So in order to find, so the unbalanced force is pretty straightforward. So these coefficient, or this constant there, is the out of balance force. And then you want to find out what's the maximum displacement, what's the x naught. So x is m naught E over m r squared. 1 minus r squared plus 2 zeta r squared. Again, r is omega r over omega n, is a frequency ratio. You can get these from lecture 9, slide 9. All right, so that's from the textbook or from the lecture notes. But then you have to change these stuff based on this problem. So your zeta is C over 2 m k. Remember, these m is the total mass. So that's why when you calculate your zeta, this m is actually 155 kilogram. It's not just the small m, it's actually everything sitting on the support. The same thing here, this m, I should use m prime. So this m prime is total mass. And then your E here is just L, or the eccentricity. Your m naught is just rotating mass. All right. Okay, so that's Q4. Anything for that problem? So Q5, I think Q5, most of you get it correctly. So there is just one thing. I'm going to emphasize this today as well. So what is your, I think the problem starts with the transfer function here. A lot of you plug these ft back into the ODE. So what you have is 2f naught plus 2x, oops, 2x double dot plus 2x dot plus 8x equal to 10 cosine omega t. And then you see, okay, there is a common 2 in both sides. You just do these, and then you saw your transfer function is 5 over s squared s plus 4. And some of you even said, okay, this is not 5 over 4, you even put a 1 on top. So I need to emphasize one thing. So when you look at your ODE function and then want to get the transfer function, you don't care about what the ft look like. You want to forget about these ft and then treat your input as a whole. You cannot substitute anything to your ft when you do Laplace transform. So that's your fs. And then on the other side, you have 2s squared plus 2s plus 8, so xs. So that means your xs over fs is something like this. So you cannot change your inputs. For example, in this case, your ft is directly given. You don't care about the amplitude of ft. That's something that won't change your transfer function. You just treat it as a whole, do Laplace transform for the entire thing, and then put it on the right-hand side. So because of that ratios issue, I think a lot of you actually had the wrong magnitude or phase lag. The other thing is, so once you have these transfer function, and then you replace s by omega j, then we call this thing called C star, right? So that's a complex number, and then the magnitude of these complex number is the ratio of the magnitude, and then the angle of these number is theta. So we already know your x naught is, sorry, we already know that your y naught, your yt is y naught cosine omega t, or I should say f here. It's just got confused. So the input ft is f naught cosine omega t. Then your output will have an amplitude cosine omega t plus theta. If you choose to use MATLAB, always remember this is going to be plus. If you use the equation in the textbook, sometimes it's minus. So personally, I recommend plus. I think next year I need to upgrade all the minus sign in the lecture notes. So this is, once you use plus, then your theta is the angle of this complex number. And the other thing is, depending on the function of the excitation, so if it's cosine, then here should be cosine. If it's sine, then the real response should be in sine. All right. I think some of you thought that x naught is sine omega t plus theta, but that's not correct, because your excitation is in cosine. So you have to use this. You have to use the same harmonic to write it to calculate the response.